Okay. So what's the fundamental question that's being addressed by these interpretations? And the question is this. You just told me that the reality is actually this craziness stuff. Wave functions and these weird elements I don't understand in this Greek letter here. But when I look out the window, all I see is, a gray elephant, an anvil, particles with, positions and momentum at the same time. So how do you get from this to this? How do you go from this description of reality to the everyday world that I see on a daily basis? That's what the interpretations of quantum mechanics are going to try to answer. So there are three broad classes of interpretation that I'm going to give tonight, and I think those are really the three broad classes that are known today. The first is called the Copenhagen interpretation. So how do we get from the wave function to the particles that we see? And the answer, the Copenhagen says that it's through measurement. If I have a weird quantum mechanical wave function and I measure the wave function, so here's my scientist waving his magic wand, maybe it's a ruler, I'm not sure, but he measures the wave function then collapses and he sees particles. So the act of measurement not only disturbs the system, but it produces some effect. It turns the wave function into particles, as it were. So what are the pros of this interpretation? Well, this is the traditional or orthodox interpretation of quantum mechanics. If you take a first-year course, a graduate course in quantum mechanics, this is the one that you'll be presented with. What are the cons? Well, there are several. Well, the first one, and the most obvious one, is this. What's measurement? What's a measurement device? I said measurement turns the wave function into particles. Well, what's measurement? I mean, is a rock a measurement device? Is a microscope? Is a cat? And they would say, and this is where, actually, this interpretation has earned the pejorative designation as the shut up and calculate interpretation of quantum mechanics. In other words, you ask a physicist about, well, wait a minute, what's a measurement device? They'll say, look, you know one when you see one. Wait a minute, but what is it philosophically? They'll say, go talk to the philosopher. This is the physics department. And that's true, and we're going to see why that's true in a minute. But one of the most radical implications of this interpretation is what I said before, is that quantum mechanics is inherently probabilistic, and objects do not have properties independent of measurement. Now, because of those two facts, many people did not like this interpretation when it was developed by Niels Bohr, among others, and they rejected it. And among those people who rejected this interpretation was Albert Einstein. He really didn't like this interpretation, and so he and others adopted what's now known as a neo-realist interpretation. Let me share a really funny anecdote about Einstein, and to show you how serious these problems were, and I'm not just exaggerating here. Albert Einstein and his biographer, Albert Peiss, who was also a physicist, were taking a walk one night, and Einstein turns to Peiss and says, do you really believe that the moon is only there when we're looking at it? And now Peiss didn't turn and say, oh, come on, what have you been drinking? Of course it's there when you're not looking at it. He didn't say that. They spent the rest of the walk discussing what it means for an object to exist. Okay? This is how radical the implications of the Copenhagen interpretation are. This is why Einstein did not like it. So what did he adopt then? He adopted something called neo-realism. Now, the pro of neo-realism is that you get to retain what's called metaphysical realism. In other words, you can still believe that particles have properties independent of measurement, which is what Einstein wanted. And you can also, to some extent, remove this intrinsic randomness associated with quantum mechanics. However, there's a big con here. In order to retain metaphysical realism and to adopt neo-realism, you basically you have to adopt or postulate the existence of undetectable pilot waves that travel faster than the speed of light and essentially backwards in time. And they travel around the universe essentially, and it's a little bit pejorative, I admit, they travel back in time, making everything look quantum mechanical. So everything's sort of really classical in nature, but there's these pilot waves that sort of make everything appear quantum mechanical, even though it's not. Again, that's a pejorative, and there are some modifications of this theory that have developed over the years, I think most notably by a guy named David Bohm. But I will say that for this very reason, this is by far the minority position among modern physicists. In fact, I've never met a single physicist who believes this interpretation of quantum mechanics, because it strikes me as completely ad hoc. He just made this up because he didn't like the implication of quantum mechanics. That's what they would say. So, it's probably a little bit even-handed here. Okay, but now if you don't like Copenhagen or neorealism, well, what's left? Well, essentially, you're left with many worlds. And if you hope to escape the weirdness of quantum mechanics with this interpretation, you're in for a shot, a rude awakening. Many worlds says this. Let's say I have a quantum coin, and it's going to state heads plus tails at the same time. And I, the scientist, am inside this quantum mechanical universe, and I measure the coin. I measure the state of the coin. At the moment of measurement, the universe now splits in two. The universe is now a multiverse with two distinct branches. In the first branch, the coin is heads, and I think to myself, oh, the coin is heads. In the second branch of the multiverse, the coin is tails, and I think to myself, oh, the coin is tails. Okay? So what are the pros of this interpretation? Well, it's nice and uniform. There's no sort of wave function particle divide. Everything is just a wave function. Everything is quantum mechanical. There's no wave function collapse upon measurement, and there's no measurement problems. Essentially, when any two particles in the entire universe interact in any way, the universe splits. Okay, so you have effectively an infinite number of parallel universes. Okay. Now, what's the con? You have an infinite number of parallel universes, and keep in mind, this infinite number of parallel universes is undetectable, even in principle. Okay, they're all there. We can't measure them. We can't detect them, but they're there. Trust us. And you could say really that if you adopt this interpretation, you really have removed the possibility of knowing anything about the real multiverse because you can only see one tiny little branch of it. And okay, I'm tipping my hand here, but if you believe this hypothesis in the multiverse, then it's really problematic, I would say, for Occam's razor. The idea that simple explanations are more likely. Well, for instance, if the multiverse hypothesis is true, then there is a universe in which I am 100 feet tall with machine gun for arms. Not there might be a universe like that. There is one branch of the multiverse. In fact, there are an infinite number of branches of the multiverse in which I'm 100 feet tall with machine guns for arms. Okay? There is a multiverse in which, or a branch of the multiverse in which unicorns exist. Okay? So again, and that's the way the multiverse works. That's problematic for most people. Wait a minute. Okay, I don't like any of these interpretations. Which is the right one? Well, that's the problem. If there was an interpretation that was normal and sane, we'd all adopt it. There isn't one. There's no satisfying interpretation of quantum mechanics that just solves all of our problems. All of them radically threaten our intuitive ideas about the way nature works. Okay. Now, what are some of the philosophical implications of quantum mechanics? And I think I've hinted at some of these already. Number one, if quantum mechanics is true, then nothing is strictly impossible. Okay? If I say to you, if classical physics were true, and I said to you, there's an apple on the table, is it possible the apple will just teleport and fall onto the ground? You say, no, that's not possible. There's 100% certainty that it'll stay on the table. If you ask me if quantum mechanics is true, which, again, everyone thinks it is, and I say, well, is it possible the apple will just teleport and end up on the table, or end up on the floor? You say, well, it's not very likely to do that. It's very, 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 very improbable that would happen, but it wouldn't violate the laws of quantum mechanics. Unless you think I'm exaggerating, this is a fascinating quote I found a couple of years ago. I'm glad I found it. A physicist who worked at the LHC, which is a Large Hadron Collider, was asked by the New York Times whether or not the collider would explode and destroy the entire world. And here's what he said. He said, well, no, I don't think it will. But, here's the quote. The random nature of quantum physics means that there is always a minuscule but non-zero chance of anything occurring, including that the new collider could spit out man-eating dragons. Now, he's making a joke. Sort of. Sort of. He said that for a reason. He's absolutely correct. That is exactly what quantum mechanics says. It's very unlikely, but it might happen. Okay. Okay, I'm going to skip causality and free will. I'm going to talk about consciousness. If you guys are fine, all right. Briefly. If you believe in classical mechanics, then there's strict order of cause and effect, right? You you have dominoes. One falls, and then the last one falls. It's just a chain of causal events leading to some effect. And so, Macbeth has the dream of the bloody dagger, he gets crowned king, he dies in the end. That's all deterministic. It's sort of not fated to happen, but the laws of classical mechanics just go from the beginning to the end, and that's what happens. There's no room for anything but determinism, okay? But that's not true because classical mechanics, as far as we know, is not true. But what does quantum mechanics say? Well, let's say we have this quantum point again, it's heads and tails, and we measure it, and it's now heads. There's the effect, heads. But what was the cause? Well, it's not really a deterministic cause anymore. We can't say what caused the measurement to be heads. So you've tinkered with the idea. This is essentially, I would say, on really, maybe realism being an exception, but definitely on Copenhagen and in many worlds, you've tinkered with the notion of causality. So you now can't say that nature is just this web of cause and effect and cause and effect and cause and effect. So for all we know, Macbeth sees the dream of the bloody dagger and then becomes a pizza delivery man. Right? And how does this provide room for free will? Well, it doesn't if. It doesn't provide room for free will if this is an entirely random process. In other words, we go from heads plus tails to heads, and it's just totally random. There's no cause of any kind. But this still leaves open the question. Well, how do you know that something didn't cause this? You can say we don't know what the cause was. But there's this sort of loophole where you say, well, I don't really know what caused this event anymore, and it's not strictly deterministic, whatever you want to say. So the bottom line is that I wouldn't say that quantum mechanics implies that we have free will, by no means. But I would say that the quantum mechanics opens up the possibility of free will when it seems like classical mechanics, at least, I would say you have to adopt the compatibilistic version of free will or compatibilist version of free will, which will. Okay, so, but it opens the door for free will. In a similar way, we talked about the Copenhagen interpretation. Now, we talked about how many physicists sort of wave their hands and say, well, I don't know what a measurement device is, go talk to a philosopher. There's a reason they do that, and that's really the way it often works in modern physics, sadly, today. The reason they do that is because if you really press on a Copenhagen person, and say, well, I want to know what measurement device is, in my opinion, there's only really one consistent stopping point, and that is consciousness. Okay? So we know there's a wave function, right? In the universe, we think there's a wave function, but we know we only see particles. So where does the wave function collapse? Does it collapse in the telescope? Does it collapse when it hits my glasses? Does it collapse when it hits my retina? Well, we're not really sure, but we're sure of one thing. I only see particles. That's a stopping point. I've never seen a wave function. No one has. And so I would say that the most consistent place to stop that chain of, well, where does it collapse, is somehow at consciousness. Now, does that mean human consciousness? Does that mean is a cat conscious? Is a bacterium conscious? Are you guys all conscious? Most of you are, I think. But again, that's the most consistent place to stop, in my opinion. Now, I didn't make that up. I didn't come up with that sort of view of the Copenhagen interpretation. Eugene Wigner, one of the founders of quantum mechanics and a Nobel laureate, said this: it follows that the being with a consciousness must have a different role in quantum mechanics than the inanimate object. So he thought that quantum mechanics implies dualism. In other words, the idea that the mind and the body are separate entities, even if they're causally linked. That was his view. John von Neumann thought the same thing, another founder of quantum mechanics. Now, I wouldn't go that far. I wouldn't say that quantum mechanics demands dualism. Again, I would say that it definitely suggests dualism. If you adopt Copenhagen, I would say it's sort of like a loophole. It's a very odd thing. It doesn't fit into our classical ideas about the universe.